Hello, welcome to Science for Free channel, and this is Muhammad Alwi. In this episode, we will continue talking about Einstein's photoelectric equation, which states that the energy of the incident photon equals the work function of the metal plus the kinetic energy of the released electron. In this video, we would like just to simplify this equation, starting from the first term, which is the energy of the incident photon. Here, the energy of the incident photon equals the Planck's constant times the frequency of the electromagnetic radiation. Let this equation be number 1. Also, as we know that the speed of the light equals the distance traveled by the electromagnetic radiation, which is lambda, or the wavelength, or the distance traveled to form one complete wave, divided by the time consumed to form one complete wave, which is the periodic time. Or in other words, we can say that the speed of the light equals the wavelength multiplied by the reciprocal of the periodic time. And as we know that the reciprocal of the periodic time equals the frequency, so we can say that the speed of the light equals lambda, the wavelength of the electromagnetic radiation, times the frequency of the electromagnetic radiation. From this equation, we can find the frequency, which is equal c, the speed of the light, divided by lambda, the wavelength. Let this be number 2. And from 1 and 2, we can deduce that the energy of the electromagnetic radiation, or the energy of the incident or the absorbed photon, equals hc divided by lambda. In this expression, we can note that hc, both are constants. H is the Planck's constant and the c is the speed of the light. Let's just simplify this in order to find a more convenient expression of the energy of the photon. As we know that the Planck's constant h is expressed in terms of, or in the units of, joule second. Planck's constant actually is a multiplication between energy and time. And also the speed of the light is determined in the units of meter per second. This means that the speed of the light is actually a length per time. So the term hc is actually energy times time times length divided by time. We cancel these times. We can conclude that the term hc is actually a multiplication of energy and length. We can express the energy in joule and the length in meter. But actually, joule and meter are not the practical units in the atomic world. So it will not be so convenient in all the calculations in the atomic world. I mean, in dealing with atoms, photons, electrons, and all this stuff in quantum mechanics. It's not so convenient to deal with the units of joule and meter. So it's much easier and more convenient to deal with the electron volt to express the energy rather than the joule, and the angstrom to express the length rather than or instead of meter. Keep in mind that 1 volt, in order to transform joules into electron volts, 1 electron volt is equal to 1.6 times 10 power minus 19 joule. And also, in order to transform the meter into angstrom, keep in mind that 1 angstrom equal 10 power minus 10 meter. And lastly, keep in mind that the electron volt is the kinetic energy attained by an electron when it's accelerated by a potential difference of 1 volt. So now, if we express this term Hc in electron volt angstrom rather than joule meter, it will be roughly about 12,400 electron volt angstrom. The energy of the incident photon or the absorbed photon can be expressed as approximately 12,000 divided by the length. Here the energy will be in electron volt, the energy of the incident or the absorbed photon in electron volt, and the wavelength will be in angstrom. This is the last equation can be used to find the energy in terms of the wavelength and vice versa. Thank you very much for watching and see you in the next video.